So good morning to all of you. So day 4 is here. Okay. So we are talking for performance-based seismic design for function. This is our Gyan course is there. So Rijit has also talked a lot about what is performance-based design is there. And he talked many equation formulations. Professor Datta sir also yesterday took quite long to teach you what performance-based design is and what perfectly it is or specifically target to what performance looking for. So precisely if you look at the performance, anything if you design it, a design if you look at, what is the outcome of the design? That is what performance you measure it. So whatever the technique or method or principle you use for the design, always looking at what is the outcome of that result is there. So here is a performance-based design, and in this one we inserted one word is a seismic design. This becomes a very important, relevant also, because when the seismic force comes, when a seismic or earthquake comes in, attack the structure, then structure goes under different kind of vibration. It faces a different setup because earthquake means thousands of frequency comings, thousands of periods are there, and structure has its own predominant time period, predominant frequency are there. Predominant frequency does mean it that what is the energy containing frequency of the ground motion, because ground motion has 1,000 of frequency, and what is a relevant period or the period in which it matches with close to the energy containing frequency of the ground motion, and if then come close to each other, then the structure faces a regress vibrations. Why it faces? If both the frequency come close to each other, both the time period of the ground motion energy containing, where the maximum energy is there, and the period of a structure, then come close to each other, then a particular type of phenomena happens. Is what is that? Resonance. That is physics you studied. Resonance. If resonance happens, what happens? Large amplitude generate. So that is what the physics is. That's comes physics in our structural engineering as well. So our objective is that as far as possible, we want to design a structure in such a way that energy containing frequency is dealing from the main structure frequency. When I say main structure frequency means the first fundamental frequency of the structure. But if your structure is have a multi-degree of freedom system, now you know all of the what is multi-degree of freedom system. So it has a multi-degree of freedom system. Then the frequency which is first emerges, that is fundamental frequency. That fundamental frequency becomes close to the frequency of the ground motion with energy content. Then because that is the which measure is contributing towards the structure response is there. The structure measure response comes the fundamental. That is why when you do analysis you carry it out, first look for the only few modes only. The modes means a particular deformed shape precisely. Modes means, if you talk about the mode means how the particular shape of the deformed structure is there. So number of modes you take it. So in a building, largely it is understood so far is that few modes is good enough to find out the response of a structure. Okay. So having said all those little background of this one, then I look at the functional recovery. Probably Arijit will speak tomorrow, so that will be better to leave it at this point. And we look at the performance-based seismic design. So having said it, next slide. So when we say all those things, that means it is precisely an engineering approach used for design and evolution of building and other structures. So we are not talking only building, but other structure. But specifically we do mention, because building is a structure which most of us frequently encounter, we see that what is going on. So it is better to focus on the building and other structure as well also. Ensure their performance and safety. When we look at the, what we are looking is the performance we are looking. Performance, that how the structure is behaving, how it has been designed, and when a ground motion comes, the seismic attacks take place, how it is going to behave it. So there are certain parameters through which we measure it. So that is what the performance is. And the structure when we design it, the main idea of focus is the structure should be safe. Rather, an engineer or structure engineer should have such a sensitivity that the structure should not fail. When we fail means we say, it's in general terms, it should not collapse it. Fail has a several degree of, but when we say that in general, they should not fail. That means no life should be lost because of your creations, engineering creation. That is a sensitivity, it's a must. That is why we look at all those parameters. That is why we measure the what is performance structure for which we have designed, it is performing or that. So that is what. So it is a general overview of what we talked so far and covering something new inside this one. So when we say this one, then the first thing which come most of the, as an engineer you look at is that you design based on the codal provisions and you try to satisfy the what codal provisions stipulates is for design is there. So the second point says this. So most of you practicing. So as far as possible, what you try to do is that the structure which has been designed should be able to stand up to the extreme earthquake. But this extreme earthquake is not for the all kind of structure, because the structure you allow certain degree of deformation or damage in the structure. So that level of damage we define. But only thing the structure which should function in all eventuality, whatever the ground motion expect is there one of them is the nuclear reactors. Nuclear reactor should not, in any eventuality, you should not fail it, because the catastrophic effect is very large. The after effect is very large. Okay. Second one is, as Professor Datta also mentioned yesterday, is the public utility. We call lifeline structures. The lifeline structure for us is the hospitals. Hospital post-earthquake should function. That means it should not, because that is the need of the people. So you have to design the structure in such a way that it should function afterwards. Okay. Third thing is a water supply line. Water supply should not rupture. It should not stop the functioning, because that is the need of the people. So certain things which function. So accordingly they have to design it. So that is how we measure their performance for which it has been designed. Okay. So this is what the little example which you focus at what means performance is when we talk about it. So normally what we doing is in the design practice, as those people whatever asked is some people have exposure that design in the practice structure, some has done the fabrication also. So what you do is mostly doing the prescriptive design is there. That is what codal based design. That is what the people accept. That is acceptable. Why the code comes in the picture? Because we standardize this thing of design process. And for anything, standardization is a must. So code is nothing but precisely a standardization. Any practicing engineer should be able to understand and implement, because once they go out of the academic institution, they will not able to do the rigorous things which you are doing, or any academician like me which we doing is not possible for them. So what they do is they have a certain set of guidelines as a form of the code, and they use the code and the design. So design which is done is a uniform or standardized one. So everybody can implement, and that is acceptable. So that is what the third point is there. So when we're doing it, the very point which is mentioned is structure will not collapse using the design level of that's for the level of earthquake. Now there is certain level of earthquake. As a common person we talk about, there are our country is concerned, we divide it into 5 zones. First zone we don't consider as a seismic zone, but remaining things we design the structure. Zone 5 is the highest level of where the northeast region or part of the Jammu Kashmir, part of the Maharashtra also fall within that range. Yes. So, that is what we say. So when we design a certain level earthquake, that means if that much is a structure encountered for which a structure has been designed, then the structure should not collapse it. So that is a mandatory requirement of the things. And that is why a uniformity is maintained. That is what the code provision comes in the picture. When we use a non-prescriptive, because most of the code is provision means most of the elastic things is the design procedure is adopted. Elastic design, when we talk about later also, I will show some slides as well, is that elastic prescription means a force deformation curve, if you consider, is a straight line. So when you expect such a large number of force due to the earthquake, because earthquake itself is not a force, it generates a force. And when you generate a force, depends on earthquake is basically oscillations, the ground oscillations, which oscillation transfer from the ground to the structure. When oscillation comes in the structure may amplify the ground motion, depends upon the characteristics of the structure, or this energy is dissipated through the certain mechanism within the building as you design it. So there are some non-prescriptive procedures also there. That means the structure not only remain the linear during the process, it also goes the non-linear deformations, and the analysis for which we have to take it. So that is also we talk about when we take some of things already done. When I mentioned, you probably will pick up that point as well. So when we doing this design procedure, the performance targets intended to current building codes is minimize life safety risk under the extreme earthquakes. When the extreme earthquake means the large number earthquakes comes when the structure should perform the function for which it has been designed. It is not going to collapse it. So this word I am repeatedly use it during this presentation. The structure should not collapse it in all eventualities. Structure should have it, because no life should be lost because of the structure or because of the creation of human beings. So your design should be meet of the standard, and why this standard comes in the picture. That is why we're talking about. Next. So some of things which I highlighted in this one. So this. So standards are not intended to provide enhanced level of performance. That means you are not expecting the performance level which you have decided beyond this going, but at least minimum for which you have designed, you should perform it. And that is what you anticipate during the process of design. Those parameters you take into account. That if this is parameter you take in, that is what the ground level motion which is expected, and according to your design. How much is linear deformation, how much non-linear deformation, at what location in the structure you're going to intend to this deformation or displacement is coming in the picture. As Professor Dattara, those places in that we understand the formation of the plastic hinge. So difference between the mechanical hinge and plastic hinge is well understood, all of you, I believe. So the second point says, this method may not fully account potential damage or loss of functionality that structure may experience during the severe earthquake. So that means they are not full damage. That is what it says is not going to perform or the severe earthquake more than what you expect is coming, because it's likely. This is a natural phenomenon which is not in anybody. So what is based on the certain scientific evolutions? Suppose you are in Jaipur, you expect based on a certain number of years what the earthquake, you know what is what data is available, so you can calculate this is level. So according to a scale up certain level, and you can design. This is the expected level of earthquake. Like in any place, that study can be done. So this is a specific study. So based on this one, you can design, and then what you expect is like this. So ultimately objective is for functional recovery, I'm speaking about this one, is that the potential downtime of critical infrastructure asset and services on which as a community we relies, it should be restored or should have a resilience in the system. That means your services should not be stopped during the process which you expect. And some of the services which I mentioned is some lifelines things which a structure need to perform is. So those services should be performed. That is what the performance-based design comes in the picture. So what is then? Last one is performance objective of a structure under the different earthquake scenario. Now earthquake scenario will also change it. So that means once we fix it, it's not going to be, it's not so. So whatever your objective you set for the design process, they should meet your standard as per your design, and they should be able to stand up what the different earthquake comes in the picture. Okay. Next. So what this performance-based seismic design says is prioritize the safety and functionality. So there are two important points comes in. The structure which you design should be safe. That is what precisely re-emphasizing again and again to you. And most of the time when I take this course, again design course, I every time I speak to student the same words is that no structure should fail. Fail means should not collapse it in all eventualities when seismic, and it should function it for which it is intended. Okay. And ultimately objective is what is again the last point. Your downtime of a critical infrastructure should function it. That means your services should not be stopped it. Okay. So this is what falls on that category of performance-based seismic design. Next. So performance-based design not only consider your structural behavior, but some of the component non-structural elements is also there. The structure have two things: structure as a non-structure. So if you talk about the building, what are the non-structural component could be? Anybody? Because later on I'm going to say something more about this part. And that the level of this, they define it, the structure performance. They say, so what are non-structure? Structure everybody says. So far is spoken about the structure. But what about the non-structure?
Those members that are not taking any loads.
Okay. Okay, what are those? Suppose a building you talk about. What are the possible things could be? Loudly. Window. Okay. But location of window is very important. When at seismic design you do it, location of window is very important. Opening rather, I would say. Opening is a very important placement in the entire structure. So that is at design level. You incorporate at design level itself. Okay. What other things? When you talk about infills also. Infills is also equally important. They are not supposed to carry any force, but the design and placement becomes very important. Third thing is there, like WT, most of you have seen it. What is part? What is peculiarity about that structure is? Cladding. One thing. What other things is there? Cladding means what? What cladding means is, yes, let's say first. Glasses. Okay. Yes. So it is a glass building precisely. So what happens? Glass. What is peculiarity? Brittle in nature. Material nature is important. Yes. The performance-based design means that two things comes in the picture. One, structure in total, the material which you use. The performance of material becomes also equally important. Yes. So that means if you glass building, that is a dangerous. Nowadays, many glass buildings are there. You look out for the green building concept also, but they are a seismic point of view, earthquake resistance point of view. They are very sensitive because if your glass falls from the 10-story building, what happens we can understand it. So that is repeatedly mentioned. That is point 6 is there. Performance-based seismic design is widely used in connection with seismic load. That is what Professor Datta also mentioned repeatedly or re-emphasize. I do the same thing when talking about the performance-based design. Particularly, it is targeted to the seismic load because the design approach. I will mention later on because then you will appreciate it. In addition to this one, dynamic, ultimately what happens is you are looking is design level. It's a dynamic behavior of structure. So dynamics need to be understood, and dynamics becomes important in other cases as well. Is that one comes in the wind, other is the blast load. So in addition to the seismic, other two loading become also equally important. Is the wind and blast load. So nuclear reactor, when we say nuclear reactor is also designed for the blast load. Okay. Likewise, people have not anticipated when the WT came down due to the aircraft hittings. Nobody has taken in the design level that such a things can happen. An aircraft may come and hit the buildings. If people could have anticipated, then they could have taken ultimately what is it? It is the impact which is coming. Apart from impact, the crude oil was there. That is a separate issue. That is a fire resistance. So fire resistance also can do it. So that is what the impact comes in. That is a plus. So now some of the structure, the people design very important structure for that much impact as well. That is the blast loading. So seismic performance is defined as coupling of expected performance level with expected level of ground motions. So how much ground motion you expect it at a place based on the scientific study which you have in it. Or if you're not available, any other available, you can scale up and can use those data for your design. Okay, next. So saying all those things, now as I mentioned, so what you expect from the structure to behave is, first thing is, structure in all eventuality it should be functional, that is operational. So facility continues in operation with negligence damage. That's damage is minimum in the structure, you don't expect. And when you say this one, what does it mean? I also wrote for you, so you have a clarity, nothing is hidden, all things explicitly is written for you. Which means that building remains occupied and operational during the earthquakes. So far I spoken, this is my emphasis was, that is what performance measure is there. Okay, so I'm slightly moving slowly away from what is Arijit and Professor Datta talk. I'm going towards the design side. Okay, so revising and taking you to slightly on this one. So this is what the fully operational. So that comes under what I asked is the service also. Service becomes equally important. Performance of the non-structural element becomes also important. Operational. When say operational, what does it mean? The facility continued in operation with minor damage and minor disruption in the non-essential services. What does it mean? So I wrote specifically for you is that the building remains essentially elastic in an earthquake. So I said earlier two things. One is elastic based design, another is non-elastic. So non-linear behavior, another is a linear behavior. So little when it comes forward, I will tell all those things as well. So with most of the earthquake, its strength and stiffness remains impact. There are two important parts of the structure when we design it. One is the strength, another is the stiffness. How strong you make the structure, if stiffness is not there, sufficient, structure will, instability will structure comes in the picture. I mentioned one. Suppose you have roof. Most of the time you go and do in the practice in the building. Suppose building is there. If it's a roof, you make it. Suppose say required is the 4-inch 100 millimeters. People say 150, 200, 250. Will it, because you have made more strength added to the floor. Okay? What the column is, the supporting system, the vertical members is, if you have a squeeze the size, what will happen? So that is where the stiffness comes in the picture. That is a supporting system that provides stiffness. So if you become unstable, stiffness is not sufficient, structure becomes a stiff. Okay? So this is what I say. When say strength and stiffness remains important, they should remain intact during the earthquake when it is operational, that is a fully functional with a little damage you allow in the structure. Okay? And building can be occupied immediately after earthquake. That is the functional, building is functional. Okay? Even though minor, so little bit superficial cracks or non-structural cracks, I would say, is there, which you can later on can depend. Building is functional, people can use it. It is purpose for which it has been designed is a fully operational. Okay? The third things, these are the level which we are going to define this. When we say performance-based design, these are the level which we have to. So, life safe. What does that mean? This life safety is a substance. That is a very important. That is, I repeat again. Life should not be lost in the all eventuality water structure. That is why we measure the performance of the structure. That is what. So, damage is moderate to excessive. That is how we define it. What does it mean is, the building sustains substantial damage in the earthquake but remains stable and with significant reserve capacity. The steel capacity is there, structure is able to sustain standard. It's not going to fall it. Okay? Occupants have an opportunity to increase the structure. They can easily can go outcome and they can use the structure. Non-structural remain secure to the structure. That's what we say, non-structural element. They should not fall. Wherever the placement is, they should remain intact in their place. They should not fall it. Okay? So that is what the level third we call is a life safe. So the last one, near collapse. Near collapse means life safety is at risk. Yes. How it is at risk, we will talk. Damage is severe and structure collapse is prevented. The structure in the last case also is not going to fall it. So that is what I mentioned. Structure in all eventuality should stand it. It should not collapse. Life of people should be protected in all eventuality. That is what the structure performance is. That is how you expect from a structure to perform it. Then accordingly you design it. So what is your outcome is there? What is your input is there? Okay? And what does it mean? Which means the building suffer extensive damage in earthquake but remains standing even barely. That means it will fall in a month, 15 days, 20 days, but it gives a sufficient warning to us. Meantime, you can evacuate the people, you can save the sufficient important things, machine or many other things which you can save it, you can take out of building. Then, so that much time is available to you. That is how do you measure the performance. So even if you to go to the last level, it is not going to collapse immediately. You give sufficient warning time. Meantime, you can evacuate the pupils. You can work. So important thing, precision things. You can talk to machine or any other things. And so that's a sufficient warning time is there even the last. So all of the level which you're going to consider, none of the level structure is going to collapse. So that is what you have to measure the performance design. That is how you do it. So this is I took this from the FEMA recommendations. So whatever we saw it, how you represent is given. This is on the EBSISA. This is precisely represent the level, expected level of earthquake you face into it. So earthquake level 1, 2, 3, 4. Some people write it. Some people have mentioned this when this earthquake is expected. Because as I said in beginning also, when you design a structure, you design for certain level of earthquake. But you have to anticipate it. The scientific study sufficient is available. Till 2001, when we have earthquake code, it was 3 pages. For top cover, bottom cover, and 1 page inside only. That was only. But after 2001 Bhuj earthquake, that is code was revised quickly and made a substantial document where people can use it for the design. And that is why where the world over the information which is available to us as a code, we take it. Nothing harm in this. Knowledge can be acquired from the all side, and we should keep open. So that is how we, most of our code is, earlier code is British based code. But now we are world over the whatever scientific knowledge is available, we, according to our need, our study, we incorporate it and we revise it. Nowadays revision in code is very fast. Earlier code used to take a very long time, 20 years or more. But Japan is very, even a Kobe earthquake came in 1995, within a year time they updated the codes. Because that is how the scientific study is drawn. So that is it's a evolving processor of knowledge. So that is how when we do the special structure, like nuclear reactor, the site-specific condition is assessed also. Because your reactor, wherever they should place it, what are the likelihood of this? So then you scale up those things, and according to design the structure. So that is how the scientific study evolves the process. So that is how the criteria is. So fully operational, what does you criteria comes, you can see it. Functionality, it has been mentioned. So it is more illustrative purpose, you can grasp the thing. Whatever I said in those text form is how they visualize a picture, which is easily comes in. Because most of human mind is, picture you quickly pick up. Even if a kid, small kid, you show the picture, he will quickly grasp it. So that is a percentage. So this is, I took it from the femur. So what is unacceptable? Acceptable. Acceptable level is there. All these things I mentioned depend upon the ground motion which I mentioned. Next. So now goes to the next slide. So having said all those things, so I highlighted the point is that collapse prevention of performance level is the must. And what is the says is, it should be subjected when the maximum considered earthquake comes in the picture. So when we design a structure, even the site-specific condition we assess it, scientific studies carried out according to synthetic, even if required, we can ground motion, we can scale up, or synthetic ground motion is also generated, and based on that, we can say the maximum likelihood of earthquake at a place is there. So MC is a very important parameter. But we do not design for MCB, we design for the certain other parameter. What is that? Is the next line is mentioned. Life safety performance level when subjected to the design earthquake. Now, design earthquake is approximately 2/3 of the MCE, maximum considered earthquake, approximately. How does it come in the picture? Anybody can guess it? Some or the other form you did it during some design level, I can say. That much hint I can give. Some factor you consider it. Say I mentioned it now. I give more hint to you. You consider partial safety of factors for structure as well as material. Partial factor is there. Now got something idea? Yes. So 0.67 means what? If you reverse it, 1.33, 33%. So that is what is approximately. So it gives a fairly fair of safety margin is 50%. So 2/3 means reverse of this one, 3/2, so factor comes out. So you have still 50% strength in the structure. If you design this one, that much performance level you expect, but in spite of that, you have to take. So even if higher level of the structure is able to sustain that much. That is why you inbuild the partial safety factor for load as well as the material. That is why you have been taught, and we are designing, whatever being taught is design practice also, same thing is being done. Same codal information is being taken. So all those things, variation, because the load partial factor for load is also taken. Why you take it for partial factor for load? Why you take it? What is need of doing that? Because suppose structure is designed for 50 years, 40 years, 100 years. the loading which you have taken is not necessarily remain throughout those periods, because that is uncertainty is associated. To account those uncertainty, this factor is included. So this factor is not come like arbitrary, some rigorous analysis has been come, and according to the factor which is generated is given in the codal form. So people can use. That is why I said code is a specific scientific document which people can easily understand it and implement it. That is why the code is there. But in every code, if you read it, the very first page, it is very clearly written that engineer which always can deviate from the what is stipulated in the code. So if you have knowledge, or you can say this is, I can deviate, you have to document, I can go. So you can do it your analysis and according to consent. So that is always. But code is most scientific, simplest document I see. So next one is that. So those are performance level, we talk 4 level, according to it has been elaborated like this one. So immediate occupancy performance. So various level of occupancy I mentioned. When subjected to frequent, so regular earthquake is coming. So not a this one D or MC what we expect, but small earthquake always come. Like in Jaipur also you feel it like that. So sometimes you don't feel it also. So frequent earthquakes. So that is what immediate performance level, that is how you classify is there. So whatever is being said is earlier, that your structure should be safe. The margin which has been incorporated, it should be sufficient to stand up the level of ground motion to consider is said. So that is what yellow I highlighted, which is important in saying in this point is. Next. So now having said all those things, what FEMA says is, it can specify in terms of lateral deflection. Now performance we say, then what is meant by performance? Like in the design which you do is the elastic design, what you do is, the highest load is there, highest deformation, that is elastic. That means the deformation you consider is elastic. When you load, you remove it, it should regain its position and becomes no deflection or deformation should be left out once the load is 0. That is elastic. But we don't do that much. There is certain things inside that. So certain purpose. Then what you do is, you bring the load down and you allow the structure to deform it. So a non-linear deformation goes. That means when you remove the load, it's not going to regain its original position, but somehow some deformation is being left out in the structure, and that is acceptable. So we'll talk that how it comes in picture is that. So these are the certain performance level you fix it. So deflection is the one of them. Drift means within the story. Within the story you measure it, that is drift. So one and same thing, that's what I obliquely put it. Deflection or drift of building. So this FEMA says the performance occupancy level is based on the overall deformation of the structure. How the overall structure, not the within the structure, the drift. Specific case, as I see Professor Datta mentioned, is one of building which was the sketch we made it, and say the plastic hinge formed at the intermediate level also, and sufficient plastic hinge has formed it. Then what happens is that becomes prone to the failure. And as I said, because sufficient plastic hinge is required, then it's called swings. The load will also move along. The additional force will generate because of that, and it becomes a susceptible region for the failure. So that's what, in that context, it becomes important. So when you do it performance, what are the things we have to object in? So you have to specify clearly. Proceed with initial design. So what you do is, most of the time you do the analysis and then finally land with the design. Okay? Now can you tell me what is the difference between analysis and design?
in analysis, our main concern is to find
Most of the time you are taught it, you do the analysis. Even practice engineer do the analysis. Then finally say this is a design. What does it mean? How you differentiate between these two? I mentioned you already. The answer is in front of you. I said proceed with initial design. When you guess you make it. You don't have anything. So you make it, and those assumptions you make it should be close to your actual, so that your iterative procedure is less number of iterations you have to do. So the final product which comes is your design. But in between you're doing. So that is a very fine difference. It is quite likely that the first iteration itself land in your final design. That depends your experience, how good you are done in this structure. That's what I say. And finally, when you do that design, then whether it meets your requirement or not, the parameter which you fix the outcome is meeting. That is what performance level you fix it. Next slide. So this is another things which I taken from the FEMA again. Now this plot, I made it. In a couple of slides afterwards I'm showing this one. How this comes in the picture. Professor Datta has mentioned this one. This is an idealized force deformation curve. It's not actual, but this is force. And this force diagram we use for the shape analysis. So today when we take some example where we're doing it, so we using this shot of the force deformation characteristics. Okay. So this is what I have taken from this one. And just we talk about what are the difference level of performance we for. So this is immediate occupancy, life safety, collapse preventions. And accordingly, this has been marked on these force deformations. So when immediate occupancy, you are here. So it is almost, you can say, the straight line. Then start little goes in the permanent deformations, and then you will almost reach to slightly lower than what the ultimate load is called, the life safety. So that is how the same deformation. The first component reaches this. That is what this level you are here. When idealized condition go, you are here. Initially you are at almost elastic range. So this is precisely called bilinear curve. Okay. When you come to collapse prevention, that means you are at ultimate stage. So you are here. When you are here, there is sudden drop of the thing, drop load will take place. Is some sort of a, if you are done the experiment in case of a bar reinforcement. Have you tested the bar in any time? No? How come? You're done? UTM?
Yes, sir.
Yes, sir.
So you pull it.
Yes.
What happens? Neck formation will take. How do you define the neck formation? Load is almost constant, not much going to differ. But your elongation is very large. And depending upon material correction, the failure will happen. Okay? So when you are here, it's similar kind. It's not exactly, I just gave a crude example of it, but once you are here, it reaches to limit, there is a sudden drop of the load is there. So in that also you see that quickly drops the load and large elongation will take place. So, but still when you are here, the structure still has a resistance approximately 20% and so. The order of it still is. That means it's not going to fall it. That's what I defined level. Still has its strength in this one. So it is not going to fall it. It's not going to collapse. So this is how this car is being used for the design purpose when we look at for performance design. So it has been. So you can easily understand what things is going on, how to use this curve, that is idealized curve for this. So next slide. So now whatever I said, this performance level is said, this precisely the point here is the formation of the plastic hinge. Okay. Now plastic hinge and you have mechanical hinge. Mechanical hinge is door is there. What is the difference between these two? Somebody I answered yesterday Professor Datta's question as well. Yeah, can you tell me? Yeah, yes, you are.
In plastic hinge, only shear is transferred, movement is not transferred.
That is fine. Yeah, that is the answer you yesterday somebody told me. But still, I want little more elaborations. Yes. Nothing. Even if you're wrong, it is okay. We all learn it. An example I said it in the door. You have a mechanical hinge. Plastic hinge forms the structure when the load comes in.
Plastic hinge has a certain capacity movement.
Yes. Okay. You come close to that one. That means plastic hinge forms due to the moment only. So plastic hinge means at a certain level of movement it rotates. Wherein the mechanical hinge zero moment. It cannot take any movements. That is major difference. So both are hinge, but there are differences there. So that is so in this case when you say the occupancy level, So plastic hinge, rotation, and rotation because we're talking about the plastic hinge, formation of plastic hinges. So these are level of, then earlier, the last slide I mentioned, all these occupancy level, how this comes in the picture. Now this is elaborated one. The graph which I have shown to you. This is an idealized force deformation curve which we use in the SAP modelings. So Shashi is there today. He will show you something in the example how to use this one and the force deformation curve. That is a push up. We apply the load and the deformation we measure. Why we call push up analysis that short up technique? Professor Datta already told you. Little I will tell when the point comes in the picture. Yes. So this curve. Now what is significance of this curve? This need to be understood. There are different level of which we talk about. So these are things which we talk about. So that is why the difference is here. So the point is here, that means no deformations. When you come here, this is a bilinear curve. So B is on, so this we call is a yielding starters. So that is what. And then it still has some reserve strength. It can go up to the maximum. That is approximately 15 to order of 15%, I can say. This slightly vary 12 to 18%, might depend on the material and all those things. So it still has a reserve. That is why this is slightly increased. Most of the time people are idealization on some of the curve which is given in the code. They do mention this, right, the straight line here, horizontal, complete horizontal. But still there's some reserve. So depends on this. So it is perfectly acceptable things is there. So this has been said. So when we hear there is a sudden drop and this. So what this inference you can draw from it, the variation each occupancy level is indicated in the figure. So these are the occupation level 1, 2, 3. Okay. The collapse does not mean fully collapse it. So when you are here, does not mean it's a fully collapse. Certain stiffness structure member is there, though there is a significant loss of the stiffness take place when you are in this region. But still the 20% strength is left out. So that means the structure is not going to fall immediately. The sufficient warning period is there. So how that curve has come. So this is a illustration is again here, and I did this to take a more clarity and understanding the performance-based design is. This is a force deformation. If a force deformation curve is understood well, the performance design is very easy task, or you can grasp it. What are your targets is, what is output is, what is input, what is output, declared. So suppose you have a building. As Professor Datta mentioned you, when using this curve, even from the code anywhere, use it as a single degree of freedom. That means multi-degree of freedom system you convert into a single freedom, and then the response spectrum you can use. So probably you started using responsive spectrum in your structure dynamics course as well. Those are, or even the code, that is the same thing is there. So when you do it, so I made it this one. So you say almost linear, and within this range, when you are here at this level, no damage. Like in earlier when the force-based design was there, still with the force design, most of you are doing the force-based design. Very few people do the displacement design. It's most of force. Little difference is there. We'll talk later on also. So what we do is then we divide by factor of safety. That's called partial safety factor, and we bring the load down, and we say this is your failure. So much strength you can reduce it, and then goes down. So that is margin you inbuilt it. So no damage in this one. When it is linear elastic, that means if load you remove it, it's going to come to this level. So no permanent deformation is left out in the structure. So when you go, there's little start things, and here, so that is proportional limit, elastic limit, that's what yield limit, and ultimate, that's what you talk about. So this is precisely same thing, precisely, but it's written in different. So when you are in this range, this is a yielding point, start it here. So when you are here from to this elastic to, so this is becomes a non-linear part, deformation. So when you remove, it is not going to regain its here, but small permanent deformation. So when you are in this, that is immediate occupancy, you call it here. That means you minor damage you have. So if you can recall the earlier slide which I shown to you, how much minor services you minor damage you acceptable, measure how much collapse then. So all those level is precisely can measure. So if in this area, only the minor damage will take place. That means minor damage means non-structural damage is going to take place. So when you go beyond, because there is still strength is there in the reserve strength, approximately order of 15%. So just beyond this one, this little away from this maximum you go, this is a life safety level which we have fixed for performance. So 3 level we fix it. So this is a life safety. So still you have safe job. Still you have sufficient reserve strength in the structure. So, and then you go, when you reach to the ultimate stage, the maximum capacity you have gone in, then this damage which is going to take place in the structure is a moderate damage which is repairable. That means what we talk on the other level, that means you can occupy the structure immediately after earthquake and you can repair it. It's not going to collapse. It's going down. So you are here in this range. So if that level you fix it, you are in this range precisely. The next is, after this one, the strength start reducing it slowly. And that is severe damage is there. The maximum, the structure damage is extensive in the structure take place. So when you do performance design, what are the performance level you are going to fix it? How much damage in the structure you are allowing based on the initial design. That means you design a structure in such a way, when ground motion come at an expected level, what you fix it, the ground motion at different level is there. So ground information, that is earthquake, also becomes important. That is one of the famous slides I show, earthquake level 1, 2, 3, 4, depends on era of occurrence and so on and so forth. So what you do is, where the allow in the structure, the damage will take place. So you, at design level itself, you can have it this in provision. Where the damage is going to take place at what place. So that portion you can later on, you can repair it or rehabilitate or retrofit it. One of the example I cited recently, if you Gandhinagar railway station, if you go in, you are Jaipur most of? Okay. Now the extensive, only a complete change is going to take place. On the entire track, you put a slab, entire tracks, and you have a vertical system column. Now as a train moves, a lot of vibration generates. That is some sort of a vibration. You have and different frequency may be there. So those vibration not to transfer to the top, because at the top you're going to have a restaurant and other occupancy also. So what they did on the top of column, they put the bearings. So those bearings will take care of the transmission of that is some sort of isolation, or will take care of the deformation which take place in this. So it will not transmit. So you can avoid this one. So this is when you are here, severe damage will take place. The already started downside, and then immediately will collapse it. So this is a collapse premature. So this is the 3 level which we talk about. If you force deformation of the entire structure you take place, this is what the pushover curve is analysis. So you push it, so this is a static, it's not dynamic again. It's an equivalent system. So Professor Datta has shown yesterday one building they push, this is precisely pushing. So you are pushing. So there is an actuator, how much you can push it, that depends upon the actuator. So it is a stroke is around 50 mm and something is order is there. So you push it slowly. So you are not applying precisely the force. It's an equivalent system. It goes and calculate it in the system, and calculate that is deformation go and calculate the stiffness. That is what I told you, the stiffness becomes important in addition to the strength also. How good strength you use, but stiffness not sufficient, the structure is not going to sustain it. So both things are equally important. So P delta, force is K delta. So P is K delta. So delta you know it, stiffness you know, it calculate it and again apply the force. So it goes further. So that is how this curve is generated. So go and apply it again, larger calculate equivalent force, in comes and apply. So that is how this goes curve. That is how this being built up is there. So that is how we are shown. So this is generated like this one. So pushover analysis, as far as Professor Datta has extensively talked, but what from the design point of view is important, which I am taking here. Little already spoken, is from the design perspective only. So, so here this is I highlighted the portion is there. So whatever the load you apply it's not a static force. It's a different. What is that? There is a motion. There is a mass. Mx double dot plus Cx dot plus Kx is equal to something. So what is Mx double dot? Inertial force. So acceleration is there, mass is there. So that is why. So it is a relative. Why it is a relative? Because inertial force we apply, it is absolute. The x which we are talking, mx dot, is absolute. Whereas in the Cx dot, where x is relative, the C comes in the picture only and only when the relative deformation comes. Else it will not come. Like in Kx also, equivalent force. So that is K also, X is when it's a relative deformation. Then K comes in the picture. Else it will not. But inertial force can come. This is absolute. Okay. So what it says, generated at locations substantial mass such as a floor. So inertial force with the mass is required. Mass is mainly at the floor. So when we take some example, the floor mass becomes equally important in the entire system. The static load pattern is increased in steps as a 1 by go. So you can say, and accordingly, there's a highlighted specific target displacement, how much going to incorporate is there. So second point also highlighted how to fixing of the target displacement. Next slide. So now having said all those things, how we go about the design is there. It being illustrated. So how you do it? The first thing is what is the capacity of the, so the force deformation curve. That is of the structure. How much? So you have a structure and this is a force deformation. So sir has yesterday also inferred. This is a spectral oscillation, it says spectral displacement. Spectral displacement and actual displacement X is the same thing. But spectral oscillation and actual oscillation is a different. There is a certain approximate relationship do exist, but there is a difference is there. So approximately, because this is close to oscillation, that is why we call it spectral. Sometimes we call it pseudo. It's not actual, but it's a pseudo. So it is there. So this is how the things is. So this is how the capacity of the structure is. So this, what we say, is this a force deformation. And sorry, spectrum is there, oscillation versus deformation. Now how much demand is there? When earthquake comes, the ground motion comes, seismic activity comes into picture. So the demand is generated, how much structure requires. And the capacity should always more than what is the demand is there. Okay? So that is how the earthquake ground motion representation comes. How much ground level of earthquake you expect it, or what ground level you are going to design a structure is there. Then that is how the demand, and according to this curve is there, which is given in the code also when you design your approach it. Those are practice it, knowing it, and those academic exercise also you know this curve is given. So that is how the demand. When you have a force deformation curve when ground motion comes, this is some sort of idealize. How do you get it? Can you know how this curve comes into picture? Can you plot it? Those how this is a smooth spectrum, because line is smoothened out. So sometimes we call it smooth spectrum also. You take an ensemble large number of 20, 100 earthquakes is there, and then you plot this this displacement versus oscillations. So all the ground motion. Then you fit it a straight line in this. So almost all earthquake will have some peak starting with from here, and then it goes down. So all this, when you plot the equation you solve, equivalent system, single degree of freedom system, then you get in this curve. So it is a smooth response. So large number of earthquake. So you cannot go to highest level also, and you are not lowest level also. So in middle of this one you have to fit. That is why you take 100 earthquakes, 50 earthquakes, or synthetic generated earthquake also depends on the place and requirement, and then you fit it. This is how in the code it has been come in the picture. It is not an arbitrary thing which has been placed in the code. A number of earthquake, they analyze it, and single degree of system, your response, you calculate it, so you cover the large number of structures, and then you put it. So when you put it together, this is a demand, and this is your requirement, capacity is there. So both you put it, then this point comes, both will cut it here. This is what your performance point, the structure should meet the target is. So this is how this design approach is there. Next slide. So I will speak only the highlighted portions. Now things come is, so far the code design are doing, or in practice also, the design which is there is a force-based design. Because force you taken as a predominant thing. Force also, when you design it, what you do using the partial of safety factor and bring down. So not only the elastic range you are doing it, that is precisely a performance design basically in the force base also. The level you fixing something else, and then you allow the non-linear deformation in the structure. So the force becomes it. Then, as we see, how much, as this one we have seen the performance point, that how much the deformation taking place in the structure. When you apply the force, the deformation in the structure is taking place. How much deformation is there? How much capacity is there? So this capacity of the structure, and the capacity depends upon how much the ductility in the structure, that is come through the stiffness of the structure. Okay, so it will deform accordingly. So how much capacity of structure, and accordingly you fix up the performance point and you design it. So here I can mention is that the parameter which you do it in the design checking. So suppose you check how much displacement is there. Like I can cite an example. Suppose beam is there, you have loaded it. And a certain guideline or exact analysis you can also do. Code says some respond to some factor is that much deformation you allowed in the structure. What is that precisely? A limit which are fixing it. So limit state is also a performance-based design because you are fixing certain limits. Like in the force base, you're fixing the certain limits. What you check it, you check the stress. You check this. That is precisely a limit which you are fixing. It should not exceed certain level. So that limit has been. So that is precisely a performance design. So this is very easy. So when most of the time European people and Asian people call this as a force-based design, but what the United States practice is that they started checking the displacement, how much. Another way of displacement is you check for the cracks also. That is also serviceability. So that is what the requirement, the limits which you fix in the design is serviceability required, where you have a displacement, you have a crack pattern. Because if cracking takes place, what happens is a stiffness goes down. So that is all. So they started calling, this is slightly moving away from this concept is displacement. So now you have a force-based design, you have a displacement. So there is a difference in the approaches there. Okay. So let us come to the point as taking the pushover analysis, where the plastic hinge considers the important part in the structure. Where the plastic, you have to design the structure in such a way, predefined location, the plastic hinge should form it. That is a, as I said, those locations at the initial level are sort of design concept, you can define where you are allowing to damage in the structure, and later on you can repair it or retrofit it. So those damage precisely comes in the picture and talk about is in form of a plastic hinge rotation. Okay, so where the plastic hinge should form it. The basic design philosophy which you understand is that the plastic hinge as far as possible should form in the horizontal members, that is in B. So column you not allowed to form the plastic hinge. And that comes through when you design this way, the weak being strong column concept. So that is also precisely a performance piece. When you do this, the plastic hinge is going to form in the beam only. Why not in the column? Anybody can tell me? Why this? Okay, I said all everybody have shaken your hands. Okay, perfectly, I said it. Huh? It's code also write it. Everything. You do like that only, but why? Yeah, no, you are coming to point. Yes.
Column should not fail because the structure might fail.
Yeah, structure may collapse it. If vertical element goes, it will not sustain. So that is why the concept is, as far as possible, you design a structure that is precisely performance. So you have to form the plastic hinge in the beam. So your design has to be. That means, other way I can say, you are predefining where the damage is to take place in the structure. That is very important. So what you say, the localized damage will take place. So useful summary of performance design is that reducing the local damage or ductility. By doing this one, what you say, how much ductility is required. So those identified place you can inbuilt in the system. So according to this, the damage will take place. So little further we go ahead, and some of the people have done extensive work in this area. So I do mention here is that so here one point becomes equally important. It is well tested thing is that frame structure behaves better in case of earthquake. And wall is there, is still improve the performance of the structure. Why? Because this is a very extensive topic, but if you go, it covers, you cannot cover in the 1 hour, 2 hour a day or something like this. So main, I want to try to cover as a very focus and main point. So you can, at least something goes in brain. Later on you can explore, depends upon what your choice is there. So, design, here I can say, when even this concept of weak beam, strong column, what happens is, it may survive in the earthquake, but some of the, depends upon, if it goes in elastic deformation, some of the time it becomes a very excessive repairing or retrofitting of this. May not be economical. In such a situation also may depend. And you need to replace entire structure also. So it is, all the time it's going to work is not there. So you have to see that when you design level, how much, how many plastic edges, what locations you're expecting it, what is sequence of formation of plastic edges is also equally important. That is what performance is. So what is, he also based on some research, he has put some his own logic and say how to reduce the repair cost also. Again, next slide. So some of things as already said, so we can skip this and we go to the next slide. Yes, next. Next slide. Yeah. Okay, this is said in other way, so we can go to next slide. Yeah, we'll go to it, but let's 5 minutes then. I understand your okay. So, Presley has done extensive work on this concept. So, if you look at this this curve, this is a moment curvature relationship. Yesterday, Professor Datta was mentioning. I think he did this either Arijit or I don't remember it. So, you see that this is a linear relationship. You take it. So, your curvature is constant almost. So whatever the level you want it, this one is there. But in the realistic conditions, if you see that this moment curvature relationship, you are going to change it every occasion. So this is a better approach than this one. Next. So last line becomes important. The force-based design is not attempt to produce a uniform risk structure. So uniformity is not there. Whereas, where this you can keep the structure below your threshold limit of the acceptance. So whatever you do it, in the all eventuality, the structure performance is going to be same in the similar condition, is not targeted in the force-based design. Where in the displacement design, this is taken care of. That's what the advantage of this. Little explanation will help you is that this bilinear curve. The first one is force-based design. The two things becomes important: stiffness and damping. These two is important parameter. While in the case of a displacement design, your yielding becomes important, and the design is based on the equivalent system. So this is a broad, if you look at what is the major difference between the force-based design and displacement approach, is this one you can look. So which curve for force displacement should appear, and what are the things which contribute is towards this. Next. Here a little, just I speak very few words. I did for the several materials. and concrete is there, steel is there. So you look at this one, the ductility which you inbuilt in the structure and the material which you use for the structure, and how much damping, because damping is very important. Damping and stiffness, that two important parameters which you'll see. So material depends upon the material used, how much damping you get, because damping will help in the damping of the forces which generated. That is important. Next slide. Okay, this is a calculation how we can skip this one. We'll come later on when take the example also. Next slide. Okay, we'll leave it this place. Okay, this is mathematics has started, so I think we stop at this. You